when we introduced the complex plane, we were talking a lot about Cartesian form numbers. So numbers that are complex can be written in the Cartesian form, defined as ZA plus BI. Well, there's also another form that we can use, namely the polar form, which is also another way of writing a complex number, which is defined as Z R times e to the power I phi. If we look at the complex plane, just at the positives of the real and the imaginary axis, if we have 1 here, we have 2, 3, here we have I, and here we have 2i. If we take a look at a number, namely 3 plus 2i, right here, then in the Cartesian way, we would define it as the real part plus the imaginary part with I added next to it. Well, the polar form actually says that from 0.0, what is the distance towards our point? This is defined as r. And the angle it makes with the real axis is called phi. And because we can go around the whole axis, phi is always between phi is always between minus pi smaller than phi, smaller or equal to pi. Now, why is I here? Why is E here? Why do we need E here? Why do we need this form? Why is it even better? All these questions, I can hear you cry through my screen. And before I can answer them, let me introduce someone very, very important. And that very, very important person is called Leonhard Euler. Leonhard Euler was one of the most proficient, if not the most proficient, mathematicians who have ever existed. He created so many proofs and so many formulas and things that after a while things were not named after him anymore because he already had so many things named after him. So they were named after the second person that proved it. So Euler's number, or E, is an irrational number, which same as pi or square root of 2, which is defined as 2.7182881. And if we create a function out of this number, let's say e to the power x, it has some very interesting properties. Namely, if we take the derivative of this function, it is the same function again. And if we take the antiderivative of this function, or we integrate it, how you want to call it, it is the same function again, of course with the constant. So this is a very, very nice function. He also had a formula which is very important to us, which is called Euler's formula. And this formula is very important. You should be able to dream it. What does it say? Well, E, which is Euler's number, to the power I is the imaginary number, which he also introduced, and x, just some arbitrary number, is equal to the cosine of x plus I times the sine of x. And this is something he proved, and this is very, very neat, because now we can link trigonometry functions like the sine, cosine, and tangent, which he also introduced, towards the E number. And the E number is needed for the polar form. And because we want to talk something about angles, trigonometry functions say something about those angles, which are very nice. And of course, with Euler's formula is another very important formula, which you should also be dreaming about, is the inverse of Euler's formula. And we have two of these bad boys. First one is for the cosine, where we take the cosine of x is equal to e to the power ix plus e to the power minus ix divided by 2. And for our another boy, for our sine of x, this one has e to the power I of x minus e to the power minus I of x divided by 2i. The proofs and the technicalities of these formulas, or how he got to those, are technically very complex, so we will not be talking about those. But these functions in itself are very, very important. These help us rewriting our Cartesian form complex numbers into a polar form. And polar forms are very neat, which I will explain later. Before we can rewrite into the polar form, let's talk about how we do it in general, and then we take an example with it. So if we have a number, a complex number of a plus bi, and you want to rewrite it into the polar form of r times e to the power I phi, we do the following. For r, we actually take the modulus of z, which we have already seen, which is the real part squared plus the imaginary part squared. That's it. That's the same as Pythagoras' theorem. Now for phi, it's a little bit different. This is called the argument of z, and this is calculated with our arctangent of our imaginary part divided by the real part. And why is that? Well, if we look at our complex plane, what does the tangent say? Well, if we have this angle here, if we take the tangent of this angle, for the tangent, it was equal to the opposite side. So in our case, it is the imaginary part of our complex number divided by the adjacent side, or in our case, it was the real part of our complex number. Now, to just get something with phi, we have to do the opposite of the tangent, and the opposite is the inverse tangent, or also called the arctangent of course, the imaginary part of our complex number divided by the real part of the complex number. Or in other words, this is also equal to b, and this is equal to a. Now the argument, when I first heard it and how to calculate it, I was very, very confused. But there are 3 methods to solve this. Method 1 is also mentioned in the syllabus. Method 2 is something that you don't really have to think about and just fill it in and you get an answer. And method 3 is something I use, which is kind of what method 1 is doing, but a little bit different. So for the argument, let's look at method 1. Method 1 states, if we want to calculate the argument of z, of our complex number, that this is equal to some cases. It is equal to the arctangent of b divided by a, only if a is bigger than 0. It is equal to the arctangent of b divided by a plus pi if a is smaller than 0 and b is bigger or equal to 0. It is equal to the arctangent of b divided by a minus pi only if they are both smaller than 0. It is equal to half of pi if a is 0 and b is smaller than 0. It's equal to minus half pi if a is 0 and b is this one was bigger than 0. So b has to be bigger than 0. For this one, b has to be smaller than 0. And it is not defined if a is 0 and b is 0, because there is no angle if we are in the origin. This is method 1. You just fill in whatever is here, and you do plus pi or minus pi depending on a and b, or you just take as half pi or minus half a pi if a is equal to 0, because otherwise you would be dividing by 0 in the denominator. Then we have method 2, which actually just solves all these cases with one formula. This says that the argument of z is equal to the arctangent, twice the arctangent of b divided by a plus the modulus of z. So actually r also in our case. And this always gives you the right answer. You don't have to think about it, you just do it. But for this you probably always need a calculator. And if you do not have a calculator, method 1 and method 3 may be better, because if you look at the trigonometry functions and the table that you really need to learn, anything that you fill in the arctangent, if it is in the table, you already know what the answer will be, which I will show you with an example later on. And we have method 3 here, which is similar to method 1, and this is a method I always use. Is if we want to calculate the argument, you always take the arctangent of b divided by a, but always take them positive. So always take take b and a always positive. Even if your number is like minus 1 minus I, just fill in 1 divided by 1. Always take them positive. And now you get an answer. And what I do, instead of remembering or trying to remember all those cases and maybe confusing with plus and minus, I look at my complex plane. If b and a are already positive, then I do nothing, because I am here in my complex plane. I am in the right side here. If I'm to the left here, it means that I have actually flipped around my angle, because I've taken my a to be positive while it was negative. So that just means that I have to do pi minus my answer. So here, in that case, you do pi minus your answer. If you are here with b and a both negative, it just means that the angle we have calculated is the same as our answer plus pi, because we can just continue going over here. This angle is the same angle it was here, but it's 1 pi further. And if I am down here, all you need to do is just take your answer negative. And in the same way, this is kind of like method 1. However, with this, I'm always looking at the plane. Where is my point? Is it both positive? I don't have to do anything. If it is in the left plane, I'm just taking pi minus my answer. If it is below, like negative and negative, that makes it positive. So I get answer plus pi. And if just my b is negative, then actually what you're doing by taking b positive is just you're flipping it around the real axis. So you just take your answer negative and you already have your answer. So this is the method I use. Method 2 works great if you have a calculator, and know that you always need to divide your answer by pi to get the exact answer. But how that works, let's look at an example. So this is how you calculate the argument. It looks very tricky, but it actually is way more straightforward than you would think. So let's take a look at an example. We have two complex numbers. We have a complex number of z, which is defined as 3 plus 3i, And we have a complex number w, which is defined as the square root of 3 minus I. For z, we want to rewrite this in the form of r times e to the power I phi. And for w, let's use different letters. So we get s times e to the power I psi. Let's both calculate for z r, which was the modulus of z, which is the square root of 3 squared plus 3 squared, which is square root of 18, which is equal to 3 square root 2. For w, for s, it is equal to the modulus of w, which is equal to the square root of 3 squared plus minus 1 squared, which in our case is exactly equal to 2. And now for the argument, which was so very complex, but actually we will see that it is not that complex. I will first use the first method. So for the first method, we just get the arctangent of 3 divided by 3, and we just have to fill this in according to the first method. Well, if we remember the table, let me rewrite it here in green in the middle, just the tangent row. The tangent of theta for each angle, for angle of 0, an angle of pi divided by 6, pi divided by 4, pi divided by 3, and pi divided by 2. Our angles were the following. For 0, it was 0. For pi divided by 6, it was 1 divided by square root of 3. For pi divided by 4, it was 1. For pi divided by 3, it was square root of 3. And for pi divided by 2, it was infinity, because you divide by 0 then. If we fill something in the arctangent, and it is either of these values that we fill in the arctangent, then we know what angle is associated with this. So right now we see arctangent of 3 divided by 3, and 3 divided by 3 is 1. So this is 1, so we know the angle of this, or the answer to this, is pi divided by 4. So this is equal to pi divided by 4. For the second method, you would use 2 times the arctangent of 3 divided by 3 plus square root of 18. And this also leaves, if you fill this in a calculator, also gives you an answer of pi divided by 4. You would get a lot of decimals in your calculator. Just divide that answer by pi and you would get 1 over 4. So you know it's 1 over 4 times pi. And for the third method, because both are positive, it's actually the same as the first method. Just fill it in, look at the table and see what the answer is. Now for w, the argument of w, if we indeed look at the first method, we take the arctangent of minus 1 divided by square root of 3. Well, because our b is negative, that meant that b is negative but a is positive. It's the same way as a is negative and b is positive, because a minus in the numerator is the same as just a minus in the denominator if you multiply both with minus 1. So that means the answer plus pi. So the answer of this plus pi, you fill this in a calculator, you would get the answer of pi over 6 plus pi, you would get minus 5 over 6 pi plus pi, close to that, no way. The answer to this, if we add pi as well with it, because it's the first method, so we add pi with this. This gives us an answer of minus pi divided by 6. If we look at the second method, then we take twice the arctangent of this, minus 1 divided by square root of 3 plus 2. And just fill it in your calculator and you would get minus pi divided by 6 as well. And if you look at the third method, it's just the arctangent of 1 divided by square root of 3. Then we look at our table and we see, well, 1 over square root of 3, that is in our answer. That's pi over 6. But because our b is negative, where are we in the plane? We are right here below, so we just have to take the negative of our answer, which is minus pi over 6, which is also congruent with the other answers. So now we have both calculated the arguments. Now we can rewrite our whole number. For z, this is equal to 3 times square root of 2 times e to the power I pi divided by 4. And for w, we can rewrite it as 2 times e to the power of minus I pi over 6. Now I can still hear you wonder, well, this is great and all, but why is this better? Well, recall how we would multiply complex numbers. If we were to multiply two complex numbers, we had all these a times c minus b times d, etc., etc. Well, all we have to do right now for z times w is you multiply the distances, so we get 2 times 3 times square root of 2 times e to the power, and we just have to add these things. So you get I, and we open up the bracket, we get pi divided by 4 plus minus pi divided by 6. So we just have to add powers and multiply only the distances, which makes it way easier. And this answer is equal to 6 square root of 2 times e to the power I pi over 12. What if you want to divide? Well, recall if you want to divide with Cartesian numbers, it would actually be a hassle. You have to multiply with the complex conjugate and everything. Well, right now, all we have to do is write down, so 3 square root of 2 times e to the power I pi divided by 4 divided by 2 times e to the power minus I pi divided by 6. And if you divide two powers, it's actually just subtracting them. So for the first one, we still need to divide the distances. So we would get 3 over 2 times square root of 2 times e to the power I. Now we would get pi over 4 minus pi over 6, which is adding them together, which in our answer will lead to 3 over 2 times square root of 2 e to the power I 5 over 12 pi. And if you're still not convinced that this is better, I'll give you the next exercise you can try out before I'll answer it. If we do w to the power 6, which would be square root of 3 minus I to the power of 6. Well, that's going to take a lot of computations. However, rewriting this in the polar form, 2 times e to the power minus I pi divided by 6 to the power of 6 is way easier, because this is the same as 2 to the power 6 times e to the power minus I pi, because if you have a power raised to a power, it's just multiplying those powers together. So we get pi divided by 6 times 6, which results in pi. And to the power 6 is actually just 64. So we get 64 times e to the power I minus pi. And I'm already done, while you're probably still working on this answer. And this makes it so much easier to multiply powers, because multiplication is actually reverted to addition, because we just add powers together. And this is a very big concept that is also used later in the course with Fourier transformations and other things in the spectral business. So polar forms are very, very important.